Over 400 million tons of plastic waste are generated each year, enough to cover the entire surface of the Pacific Ocean for at least the next 500 years if no effective treatment measures are taken. As environmental pollution becomes increasingly complex, recycling emerges as the most critical key to unlocking the era of the circular economy, where humans and advanced technologies work together to turn plastic waste into massive economic value while reducing its destructive impact on global ecosystems. The plastic recycling industry alone generates over $60 billion annually, with recycled products permeating nearly every aspect of daily life. In today's video, join Agriculture Insight as we explore massive plastic waste sites and step inside modern recycling plants, where millions of new plastic bottles are produced every day from discarded plastic, helping shape a more sustainable future for our planet. All will be revealed right now. The journey of plastic recycling begins the moment empty bottles are discarded, after they have fulfilled their original purpose. From crowded supermarkets, schools, and offices to small residential neighborhoods, millions of plastic bottles are collected every day through recycling bins placed everywhere. However, not all places operate in the same way. In the United States, only 10 states, such as California, Oregon, and Michigan, apply a deposit refund system. Under this system, consumers pay a small deposit when purchasing bottled drinks and receive it back when they return the empty bottles. Thanks to this mechanism, the recovery rate of plastic bottles in these states is twice the national average, turning used bottles into items with cash value the moment consumers finish drinking. After that, teams of workers and specialized trucks travel throughout the city, collecting sacks full of plastic bottles and compressing them into massive containers. Each truck can carry tens of thousands of bottles, equivalent to about 20 tons of plastic in a single trip. When arriving at transfer stations, the entire load of plastic bottles is unloaded in just a few minutes through conveyor systems or tipping mechanisms. Dozens of tons of plastic bottles cascade into the collection yard, forming enormous mountains of plastic that shimmer under the sunlight, blending shades of green, blue, transparent, and many other light hues. These huge masses of raw material are then fed into processing lines, where modern technology begins transforming waste into clean material, ready for a new life cycle. To transform chaotic piles of collected plastic bottles into a consistent material stream, recycling facilities rely on a preliminary sorting stage where human labor and technology work closely together. Although 7 major plastic types exist, each marked by a recycling symbol, only PET and HDPE are commonly recycled into new products at scale. Therefore, the entire system is designed to preserve these 2 plastics while removing unsuitable materials as early as possible. The process begins when mixed plastic waste enters a massive rotating steel drum, perforated with rows of holes. As tons of bottles and packaging tumble inside, dirt, sand, and small debris fall through the openings, while larger plastic items continue moving forward. This step separates materials by size and prepares them for more precise sorting downstream. Next, conveyor belts carry plastics through manual sorting lines. Workers stationed along both sides quickly remove contaminants such as metal cans, plastic bags, and cardboard. At the same time, automated cutting blades detach caps and labels, often made from different plastics. Magnetic sensors extract small metal fragments like staples or leftover can lids. After this combined screening, the material stream becomes uniform, consisting of PET bottle bodies that are cleaner, purer, and ready to enter the next phase of the recycling journey. After sorting, rigid plastic bottles are fed into a shredding chamber where hundreds of alloy steel blades spin at extreme speed, producing a sharp, piercing noise that echoes through the factory. In moments, each bottle is ripped into countless uniform fragments only a few inches long, small enough to slide along the conveyor like a stream of glittering plastic sand under bright lights. The sheer power of these machines is astonishing. Each hour, they can process up to 3,000 pounds of plastic, quickly transforming mountains of bottles into tidy flakes within minutes. Shredding does more than reduce size. Finely chopped plastic melts far faster inside the extrusion furnace, saving up to 40% of energy compared with melting whole bottles. As a result, the entire production line runs faster while significantly lowering operating costs, creating a strong foundation for the next stage of high-tech sorting. This efficiency makes large-scale plastic recycling faster, cleaner, and more economically sustainable worldwide today. From these tiny fragments, optical technology and artificial intelligence handle the most delicate sorting stage of the entire process. A network of high-speed cameras scans each piece, analyzing color and surface structure within milliseconds. When the system detects clear PET, blue PE, white PE, HDPE, or foreign materials such as wood, ceramic, or glass, a burst of compressed air is instantly triggered, blowing that fragment out of the main material stream. The accuracy is astonishing. Each air jet targets a single plastic piece weighing less than 1,000th of an ounce without disturbing neighboring fragments. On average, an optical sorting machine can process more than 10,000 pieces per second with over 95% accuracy, equivalent to the output of hundreds of workers operating continuously without rest. Every second, tens of thousands of particles are separated precisely, forming streams ready for next stage. From the initial state of chaos, the material fragments are now pure enough to enter the pelletizing stage. After sorting, plastic flakes are fed into an extrusion system, where temperatures rise beyond 520 degrees. Under this intense heat, each fragment melts and blends into a thick plastic flow, moving forward like a stream of artificial lava. Inside the machine, a massive screw rotates continuously, mixing the molten material while steadily pushing it ahead. As the plastic travels along the length of the screw, pressure gradually increases, forcing the melt forward. When the material reaches the desired viscosity, it is pushed through ultrafine metal screens that trap the final impurities. At this stage, the molten plastic is cut into countless tiny pellets and immediately cooled with water to solidify their shape. Uniform in size, smooth-surfaced, they sparkle like gems. From uniform PE pellets, the manufacturing journey moves into a defined stage. Preform production, the foundation on which the final shape of the product is created. Inside the factory, material that has passed quality inspection is fed into a heating system, where temperatures rise to around 480 degrees, softening the plastic and preparing it to flow into molds. The result is a short component shaped like a test tube, known as a preform. Each preform has a thick body, while the neck is already formed with threads for a cap. Designed to withstand high temperatures and mechanical pressure, preforms maintain stability throughout transportation and subsequent processing. The advantages of preforms are not limited to technical performance. Their compact size optimizes storage and logistics, allowing millions of units to be transported efficiently without occupying excessive space. For this reason, many facilities specialize solely in preform production, supplying beverage companies, where they are blown into finished bottles closer to points of consumption. When the preforms are ready, they enter a decisive stage, blow molding, where they take on the true form of a plastic bottle. The preforms are fed into a heating system, warmed just enough for the plastic to become flexible while maintaining structural stability. Immediately afterward, high-pressure compressed air is blown in through the neck, causing the plastic walls to expand evenly and press tightly against the metal mold surface, precisely engineered to the desired shape. A 1.5-liter bottle preform, initially only about 10 to 12 centimeters long, can stretch 4 to 5 times its original height during the blowing process. This technique is considered one of the most precise and highly automated stages in PET bottle manufacturing. Each system can produce thousands of bottles within seconds, with deviations controlled to minimal levels. Wall thickness, cap thread accuracy, concentricity, and surface gloss are continuously monitored by sensors and computer software. The result is a lightweight bottle that remains strong enough to hold carbonated beverages, resist leakage, and maintain its shape under pressure. Beyond meeting technical standards, this process offers remarkable flexibility. Bottle volume, body curves, label placement, and even embossed logos can be customized to meet brand requirements. It is here that a simple plastic preform is transformed into a complete PET bottle, ready for cooling and packaging. Immediately after leaving the blow mold, the bottle surface remains at very high temperature, making the plastic walls soft and easily deformed if not treated at once. For this reason, production lines guide bottles into an instant cooling system. Streams of cold air or circulating water stabilize the bottle structure. This rapid cooling process allows the material to harden quickly and retain its original shape. Notably, in modern factories, cooling speed is calibrated with extreme precision. A newly formed PET bottle can reach a safe temperature in under 5 seconds. In addition, many systems recover heat released from bottles to warm water or air, saving energy and reducing operating costs. Once the plastic has fully solidified, the bottle gains mechanical strength needed for stacking, labeling, and withstanding impacts during transportation. Cooling time is calculated to avoid slowing production lines while ensuring clarity and rigidity. When the bottle body is fully stabilized, the journey continues with a rigorous inspection stage to ensure quality before the product reaches consumers. The inspection line is equipped with sensors, cameras, and high-precision measuring devices. Each product is scanned to detect cracks, air bubbles, or dimensional deviations. In addition, random samples undergo mechanical tests such as tension, compression, and impact to evaluate strength. For bottles intended for food and beverages, laboratories conduct chemical analysis to ensure no harmful residues remain. Only after passing this entire strict sequence of checks is the product allowed to move to the next stage. Approved bottles are grouped into large batches, stacked on pallets, and wrapped in protective film. Automated robotic pelletizing systems arrange thousands of bottles, containers, or plastic products neatly and accurately. Each batch is labeled with traceability codes, ensuring full transparency from recycled raw materials to finished goods. Products ship from warehouses, completing a circular journey. In the United States, the reality of plastic recycling contains many darker sides than labels often suggest. Only about 5% of plastic bottles are actually recycled, while most of the remainder is buried in massive landfills or sent to incinerators, continuing to place heavy pressure on the environment. For many years, the United States, along with other developed nations, relied on exporting millions of tons of plastic waste to Asia, with common destinations including China, Malaysia, Vietnam, and Thailand. However, in 2018, when China issued a ban on plastic waste imports, that door suddenly closed, forcing the United States to confront the enormous mountains of waste it had created itself. Even so, some plastic continues to be shipped to other developing countries, where waste management capacity remains limited. As a result, large quantities of waste are discharged directly into rivers and oceans, further fueling a new wave of global pollution. This practice worsens ecosystems and threatens wildlife across continents worldwide and future human health. Few people realize that glass, an everyday familiar material, is placing growing pressure on global natural resources. Creating it from scratch comes at a high cost. Billions of tons of sand are dredged every year, causing severe erosion and damage to river ecosystems. Beyond the massive energy consumption and CO2 emissions, impurities in raw sand are also a #1 enemy, aggressively corroding the refractory bricks of million-dollar furnaces. That is why glass recycling has become a key solution for preserving this precious resource. Environmental leaders such as Switzerland and Germany have now reached recycling rates of up to 90%, 3 times higher than that of the United States. Why do you think this enormous gap exists? Many people wonder whether recycled glass is truly clean enough for food use, but the truth is that it is just as pure as new glass. Unlike plastics or rubber, which can easily undergo structural changes, glass is completely inert. It does not absorb odors, does not retain color, and most importantly, does not release any microplastic particles into the human body. That is why, at the strictest frontiers, such as vaccines and high-grade pharmaceuticals, the world still has no perfect substitute for glass, a gold standard for human safety. And now join us as we explore this remarkable rebirth, a journey that may seem vast in scale yet begins in the simplest of places, the household waste bins of millions of families. For this circular process to begin, the first requirement is a stable supply of used bottles and jars. In modern recycling systems, collection largely relies on fleets of specialized trucks, machines designed exclusively for glass. On average, a major operator such as Biffa in the United Kingdom must cover around 3,000 households per day to ensure not a single fragment of recyclable glass is left behind. This pressure becomes even more intense during the summer months, when warmer weather drives up demand for cold beverages. The resulting surge in discarded bottles and jars forces collection trucks to operate at full capacity, making multiple collection rounds per day instead of the usual single run. But door-to-door collection is not the whole picture. In most EU countries, networks of reverse vending machines are now installed throughout supermarkets, activating source-level sorting right at the point of disposal. Consumers simply place an empty bottle into the machine. The system scans it, sorts it, and returns a small cash refund, typically around 10 to 25 cents, depending on the country. A soda bottle you've just finished drinking, instead of becoming waste, can instantly turn into loose change for your next purchase. This approach not only encourages people to participate voluntarily in collection, but more importantly, it supplies recycling plants with a stream of pre-sorted, cleaner, and far more uniform glass than ordinary mixed waste. From here, the journey of transporting tens of tons of bottles and jars to specialized processing plants begins. Large trucks, each capable of carrying between 20,000 and 30,000 bottles per trip, operate continuously, moving between supermarkets and collection points to consolidate the material for recycling. The processing cycle is formally initiated when heavy-duty industrial loaders move in on stockpiles of waste glass rising several meters high. Each bucket can hold multiple tons of material, which is transported in a controlled manner across the yard to maintain a steady feed rate into the plant. At the intake point, the glass is discharged directly into receiving hoppers. Driven by gravity, the mixture of fragments slides down reinforced steel chutes where conveyor systems come into operation. From this moment on, the glass stream, still mixed with sand, dust, and contaminants, is carried deep into the processing line, where successive stages of cleaning and sorting will ultimately determine the quality of the entire downstream recycling process. After being broken down, the waste stream makes its first stop at a multi-stage vibrating screening system. Here, high-frequency vibrations separate natural contaminants, such as dust, gravel, and sand, from the main glass flow. This stage serves as a surface cleaning step, allowing the material to be more clearly exposed and prepared for more advanced sorting processes. However, mechanical equipment at this stage cannot fully remove larger or lighter contaminants, such as paper labels, plastic films, or pieces of wood. As a result, a manual inspection zone follows immediately after the vibrating screens. Specialized workers are positioned along the conveyor belt to visually monitor the stream and manually remove any remaining foreign objects. The combination of mechanical separation and human judgment ensures that the material meets cleanliness standards before entering the more sophisticated downstream separation systems. But even after screening and sorting, troublesome obstacles always remain hidden within the pile of broken glass. Bottle caps. These are the enemies of the furnace, as they do not melt like glass and instead introduce contaminants capable of ruining an entire batch. At this stage, massive electromagnets suspended above the conveyor belt come into operation. Generating extremely strong magnetic fields, they lift and extract every steel bottle cap or screw upward, completely separating them from the glass stream moving below. Thanks to this decisive step, the cleanliness of the material is raised to around 80%, clearing the way for the critical crushing stage that follows. Once most contaminants have been removed, the glass enters a critical stage of structural transformation. Crushing. Large fragments are fed into hammer mills where high-speed rotating hammers deliver repeated impacts, breaking the glass down into uniformly sized particles. To maintain quality control, any pieces exceeding the specified size are captured by screening systems and redirected back into the crushing chamber. The result is glass cullet with a fineness comparable to manufactured sand. Reducing glass to this granular form not only allows it to melt more quickly in the furnace, but also helps save up to 40% of the energy required compared with using entirely virgin raw materials. Immediately after crushing, the material stream is passed through a high-capacity extraction system. Here, powerful air currents strip away and blow off any remaining microscopic label fragments still clinging to the surface. This final cleanup step ensures the glass reaches maximum purity before entering the laser-based sorting stage. The final, and also the most sophisticated stage in the cleaning process, is optical sorting. At this point, glass fragments are spread thin and allowed to fall like a waterfall in front of a system of high-power laser sensors. In a split second, these sensors scan each fragment to accurately analyze its color and material composition. As soon as a differently colored piece of glass is detected, or more dangerously, a stray piece of ceramic, the system immediately activates compressed air nozzles. These air jets fire with millimeter-level precision, blowing the contaminants out of the main stream in just milliseconds. Absolute precision at this stage is vital, because even a tiny amount of color deviation or ceramic contamination can completely ruin the transparency and quality of the entire batch. After passing the laser system's inspection, the clean glass fragments move along the conveyor belt to the final collection area. Here they are separated and stored individually according to 3 color codes: clear, green, and brown. A step that may seem simple, but in fact directly determines the value and efficiency of recycling. Few people know that clear glass accounts for the largest proportion and has the highest economic value. However, with just 1% colored glass mixed in, a melting batch will immediately become cloudy and unable to regain its original transparency. Therefore, color separation is mandatory to control purity, enabling factories to recycle directly into new products of the same type without incurring the cost of removing color impurities. After being refined, recycled glass cullet cannot be fed directly into production, but must first go through a raw material blending stage. The basic composition starts with pure silica sand to ensure transparency. Next comes soda ash to lower the melting temperature, and limestone to increase the mechanical strength of the finished product. Depending on specific requirements, manufacturers add minerals such as alumina, dolomite, or metal oxides to adjust color and physico-chemical properties. In this batch mixture, recycled glass accounts for 20 to 70% of the total weight. This proportion allows the mixture to melt faster, directly saving about 40% of operating energy and reducing carbon emissions compared with using only virgin raw materials. Once the components reach the standard proportions according to the preset formula, the mixture is thoroughly blended and moved to the melting stage. The batch is fed into a high-capacity gas-fired furnace system. Here, the temperature is maintained at around 1,250 degrees Celsius to carry out the material transformation process. Because the heat radiated into the surrounding environment is extremely intense, the operating crew must wear specialized heat-insulating protective clothing and thick gloves to control the melting pot safely. After about 24 hours of continuous firing, the raw material mixture melts completely and turns into a highly viscous liquid. During the next 5 hours, the molten glass is kept at a stable temperature for the refining stage. This is a mandatory step that allows air bubbles to escape, ensuring the purity and uniform structure of the glass stream. To transform the molten glass stream into products with specific shapes, the mold system is an indispensable component. Based on designs created in specialized CAD software, molds are manufactured from cast iron or special alloy steel. These materials possess extremely high heat resistance, up to 1,400 degrees, ensuring they do not deform when in continuous contact with molten glass. After fabrication is completed, the mold sets are installed on the production line, ready for the forming stage carried out directly inside them. When the mold system is ready, the process enters the double blow stage, the standard method for producing hollow containers such as soft drink bottles or pharmaceutical jars. The process begins by cutting the molten glass stream into gobs of uniform weight. These gobs enter the preliminary mold at around 1,000 degrees Celsius, the ideal temperature at which glass reaches stable viscosity, allowing smooth forming. Inside the preliminary mold, a first blast of compressed air is blown forcefully from above, pressing the molten glass tightly against the mold walls. The result of this step is the formation of a parison, a hollow structure in which the bottleneck is clearly shaped, while the body remains soft and retains a large amount of heat. Immediately afterward, the glass parison is transferred to the final mold set, located right next on the production line. Here, a second blast of compressed air is injected directly into the center of the parison, stretching the softened glass outward until it fully conforms to the fine details inside the mold cavity. Although this process appears very fast from the outside, in reality, the entire system of valves and sensors must be synchronized with precision down to 1/1000 of a second. It is precisely this extreme level of technical control that enables corporations such as Coca-Cola or Heineken to ship hundreds of thousands of bottles every day with absolute uniformity, ensuring that every single bottle meets the same standards before global distribution. Although today glass packaging accounts for only about 15% of Coca-Cola's total output, it is by no means outdated. On the contrary, for many discerning consumers, glass remains an irreplaceable choice. It keeps drinks cold longer, does not retain odors, and does not alter flavor. As a result, the fizz and sweetness are preserved intact, a purity that plastic or aluminum has yet to fully replicate. Now, let us explore one of the world's leading sisal-producing countries. In northern Tanzania, around the regions of Tanga and Morogoro, where rainfall lasts for only 3 to 4 months a year, sisal has not merely survived, but has dominated the agricultural landscape for more than a century. Sisal is typically planted at the beginning of the rainy season in March on gently sloping land where water does not stagnate, yet retains enough moisture for young plants to establish themselves. Seedlings are planted directly into the soil, spaced at approximately 1 meter apart, allowing their long, thick leaves to develop to full capacity. During the first 2 to 3 years, sisal requires very little intensive care. Thanks to a root system that penetrates several meters deep and a natural water storage mechanism within its leaves, the plant can thrive with annual rainfall of around 700 millimeters, significantly lower than that required by most industrial crops. It is precisely this paradox, minimal care combined with long-term productivity, that makes sisal an ideal crop for semi-arid agricultural regions. Have you ever noticed how sisal looks remarkably similar to a plant commonly used to make spirits? In fact, Sisal belongs to the same agave family as the plants used to produce tequila and mezcal. However, while agave grown for spirits is cultivated to harvest the sugar-rich core at its center, Sisal follows an entirely different path. It is grown to extract fiber from its leaves. This fundamental difference shapes every aspect of how Sisal is cultivated and harvested. After approximately 3 years of growth, Sisal enters its harvesting phase. The plant is not cut down. Instead, it is harvested repeatedly in cycles, a process that can continue for nearly 10 years. During each harvest, workers cut only the outer, mature leaves, where fiber concentration is at its highest. The central core and young inner leaves are left intact, allowing the plant to continue growing. Sisal leaves are cut close to the base using specialized knives. A harvest-ready leaf is typically over 1 meter long, thick and rigid, and heavy with moisture, requiring a firm, decisive cut to avoid damaging the fibers inside. Over its lifetime, a single Sisal plant can produce more than 200 leaves, though only a portion is taken during each harvest to prevent exhausting the plant. Once cut, the leaves are laid out directly in the field, where overly young or damaged leaves are removed. Leaves that meet quality standards are then bundled uniformly, prepared for the next stage of the production chain. On average, a single worker can harvest more than 1 ton of Sisal leaves per day. And on large plantations, total daily harvests can reach tens of tons. When Sisal leaves enter the factory, the fiber extraction process begins immediately and runs continuously. The leaves are placed parallel on a conveyor belt, with their tips directed toward a set of pressing rollers that use mechanical force to keep them straight and stable. The conveyor then feeds the leaves into the decortication machine, where high-speed rotating drums crush the leaf pulp and separate the long fibers inside. The pulp and plant juice are expelled at the decortication chamber, while the raw fibers continue forward, retaining their full length. A standard production line can process 20 tons of leaves per hour, yet the output is highly selective. Only about 4% of the leaf's weight becomes usable fiber. The raw fibers then pass through a continuous washing system to remove sap and plant residues, before undergoing preliminary combing to separate and straighten the strands. Within just a few minutes, a fresh green leaf is transformed into raw fibers, ready for the next stages of processing. After washing and preliminary combing, Sisal fibers enter the drying stage, a critical step that determines both color and durability. The fibers are spread out or hung evenly on drying racks, ensuring they do not overlap so moisture can evaporate uniformly. In major production regions such as Tanzania and Brazil, Sisal is typically sun-dried, where ambient temperatures average around 30 to 35 degrees Celsius. The drying process usually lasts 2 to 3 days, until the moisture content of the fibers drops below 12%, a safe level for storage and further processing. If drying is insufficient, the fibers may darken, lose strength, and become more susceptible to mold. After drying to the required standard, Sisal fibers are collected directly at the drying yard, the moment when the fiber's final form first becomes clearly visible. The fibers are removed from the racks and carefully recombed to eliminate short strands, sand, and remaining impurities. They are then graded by length, color, and uniformity. From over 1 ton of fresh leaves, only around 40 kilograms of usable fiber remain, bundled into 20 to 25 kilogram bales. This is the critical stage where raw mass is refined into true value. After being delivered to the factory, Sisal fibers are fed into an industrial rotary drum combing machine to clean and even out the fibers. Inside the machine, steel rollers fitted with metal teeth rotate continuously at a speed of approximately 400 revolutions per minute, pulling and aligning the fibers in a fixed direction. This process straightens the fibers, separates tangled bundles, and removes short fibers and residual debris. The spacing between the rollers is precisely calibrated to just a few millimeters, sufficient to clean the fibers thoroughly without breaking the long strands. Immediately after combing, the sisal fibers are transferred directly to a hydraulic baling press. Here, the fibers are compressed into standard bales weighing approximately 25 kilograms, reducing volume and stabilizing their shape. The baling stage marks the end of fiber processing within the factory, transforming loose sisal fibers into a complete raw material unit ready for the next stage of spinning. At the spinning mill, sisal fiber is not fed directly into the twisting process. The first step is fiber alignment. Bundles of fiber are separated, stretched, and arranged parallel along a single axis. This step eliminates the natural misalignment of plant fibers, the primary cause of fiber breakage if twisting begins too early. Once the fibers are aligned in the same direction, primary twisting begins. At this stage, the fibers are lightly twisted at a density of around 100 twists per meter, just enough to form a stable single yarn. The goal is not strength, but to prevent the fiber from separating during further processing. Next, the single yarns are plied and subjected to secondary twisting. Depending on the intended application, sisal may be spun into 2-ply or 3-ply yarns. Increased twist density locks the fibers tightly together, creating a structure capable of bearing load and resisting abrasion. Even a small deviation in twist level can reduce the fiber's service life in real-world use by up to 40%. At the end of the spinning process, sisal yarn is twist set and strength tested, then graded and sent on to subsequent stages, most commonly rope making. And now, sisal yarn enters the rope-making stage, where a single strand is transformed into a fully load-bearing structure. The process begins with strand assembling. Multiple spun yarns are fed in parallel into the machine and held under controlled tension before moving into the next twisting phase. This is followed by cable twisting. The strands are twisted in the opposite direction of the original spin, balancing internal forces and preventing the rope from unwinding under load. Depending on the design, sisal ropes typically consist of 3 strands, each made up of dozens of finer yarns. This multi-layered structure allows the rope to distribute stress evenly and improves resistance to abrasion during use. Once the required twist is achieved, the rope is set and continuously straightened over lengths of up to 200 meters in a single production run. Even minor deviations during twisting can create localized weak points. For this reason, finished ropes undergo load testing with tensile strength capable of exceeding 1 ton before being cut, coiled, and packaged. At this point, Sisal completes its journey from a plant-based fiber to a reliable load-bearing tool used across everyday life and industry. The journey of Lotus fiber follows a completely different path, more meticulous, more labor-intensive, and far more delicate. Lotus stems are typically harvested between May and August, when the plant is at its peak growth and the fiber content inside the stem is at its optimal condition. The ideal time for harvesting is early in the morning, when the stems are still fresh, rich in natural sap, and have not yet been dried by the sun. If harvested at midday or in the afternoon, the fibers inside quickly lose their elasticity, making them extremely difficult to extract. After harvesting, the lotus stems are washed thoroughly before any further processing begins, in order to remove mud and impurities, and to keep the stems fresh so the fibers are not damaged. The extraction of lotus fiber must be carried out within 6 hours after harvesting, while the lotus stems are still fresh and rich in natural sap. First, the stems are cut into short sections of about 20 centimeters, a length suitable for hand processing. Each section is then gently broken open, exposing the fine fibers hidden inside the stem. From each section, the artisan typically pulls out around 10 extremely delicate fibers, almost transparent and very easy to break. These fibers are too short to be used individually, so they are joined together by hand, lightly twisted between the fingertips to form a continuous thread. Throughout the process, the fibers are kept slightly damp with water, which helps maintain flexibility and prevents breakage. The entire operation is slow and entirely manual. On average, a skilled worker can extract about 200 meters of lotus fiber in a single day. If the stems dry out or the movements become too forceful, the fibers quickly become unusable. After spinning is completed, the lotus fiber enters the winding stage, the final step before weaving. At this stage, the fiber is guided through a winding machine to control both tension and direction. The machine keeps the fiber under just enough tension, preventing sagging, misalignment, or overlapping as it is wound. The winding process moves very slowly, as lotus fiber is extremely fine and fragile. Any sudden increase in tension can cause the fiber to break at its weakest point. During a stable run, the fiber can be wound continuously into a spool of approximately 150 meters, sufficient for use as warp yarn on a traditional loom. If the fiber is unevenly distributed, or the spool becomes misaligned, the entire roll cannot be used for weaving. For this reason, the artisan must constantly observe the process, adjusting the hand crank and machine speed. It is at this stage that loose lotus fibers are transformed into ordered spools, ready to enter the demanding process of lotus silk weaving. When the lotus yarn spools are ready, the process of weaving a lotus silk scarf begins with loom setup. The lotus yarn is stretched as warp threads on a traditional hand loom, one strand at a time, with tension carefully calibrated to keep the fabric surface even. If even a single thread is misaligned, the warp can break during weaving. During weaving, the artisan opens the heddles to separate the warp threads, passes the weft yarn through the opening, and then beats very gently to secure each row. Every movement is slow and deliberate, as lotus fiber is extremely fine and brittle. In a single working day, the weaver may need to stop hundreds of times to repair broken warp threads, something that rarely occurs when weaving silk from silkworms. Each repair requires precise tension, otherwise the fabric surface will be flawed. At this pace, completing one lotus silk scarf typically takes around 7 consecutive days, with less than 1 meter of fabric woven per day. This slow, high-risk process, entirely dependent on skilled craftsmanship, is what drives the price of a lotus silk scarf to between $300 and over $1,000 USD, making it a textile that is nearly impossible to mass produce. For premium bamboo straw products, only young, straight bamboo stalks with small diameters, typically 1 to 2 centimeters, free from cracks or insect damage, are selected. Next, each stalk is measured and cut to the standard length of 18 to 20 centimeters, then polished both inside and out using rotary sanding brushes to create a smooth, splinter-free surface that is safe for use. After sterilization and drying to reduce the moisture content to 10%, each straw is individually inspected, laser engraved with branding, and packaged in biodegradable paper sleeves or reusable fabric bags, ready to replace single-use plastic straws in cafes and restaurants around the world. However, natural bamboo straws currently account for only about 3 to 5% of the market, while bamboo fiber straws make up more than 20%, an industrially produced alternative that you'll see the manufacturing process of later in this video. On each bamboo board, hundreds of spoon and fork templates are pre-programmed into computer systems and precisely cut using laser beams or high-pressure water jets, ensuring smooth edges and consistent thickness. The cut bamboo blanks are then transferred to polishing machines, where their edges are rounded, surfaces are smoothed, and any sharp corners are removed. After being soaked in vegetable oil or coated with natural wax, the spoons and forks are tested for strength, heat resistance, and surface smoothness before being packaged and prepared for distribution to the market. The process begins by cutting the bamboo into blocks and shaping them into smooth rectangular handles using automatic molding machines. For premium models, CNC machines are used to create ergonomic curves or grooves that meet dental design standards. The most intricate stage is bristle installation. Tiny holes are precisely drilled into the toothbrush head, where biodegradable nylon 4 or plant-based bristles are securely anchored using micro stainless steel pins or natural adhesive. Finally, each toothbrush is polished again, inspected for smoothness, and packaged in recycled craft paper or biodegradable boxes, offering a sustainable alternative to plastic toothbrushes, combining durability, hygiene, and a modern, eco-friendly design. In modern factories, high-efficiency production lines can produce around 3,000 bamboo toothbrushes per day, but compared to more than 3.5 billion plastic toothbrushes consumed worldwide, that number is still very small. In the United States alone, over 35 million tons of plastic waste are generated each year, while eco-friendly products made from bamboo and other natural materials account for less than 5% of the market in the country. Could you explain the reason behind that? A more advanced version of bamboo material is strand-woven bamboo, a type of material made from bundles of bamboo fibers instead of whole culms or traditional strips. After being cut and carbonized, the bamboo is not split into strips but rather crushed or separated into long fibers, then dried and mixed with bio-based adhesive or heat-resistant resin to create bonding. When reaching the ideal moisture level, the fibers are evenly layered, each layer arranged in a different direction to enhance strength. These layers are then pressed in a high-temperature hydraulic press to form dense strand-woven bamboo blocks. Thanks to its fibrous structure, this material has mechanical strength up to 25% higher than oak or teak, while being almost completely resistant to cracking, bending, and moisture, with an average price of $1,900 to $2,000 per cubic meter. After cooling, the bamboo blocks are planed, cut, sanded, polished, and coated with natural oil or wax to protect the surface, giving them a service life of up to 25 years. Today, strand-woven bamboo is widely used in high-end furniture, industrial flooring, and sustainable architecture. The global bamboo materials market is currently valued over $70 billion USD, with laminated and strand-woven bamboo accounting for nearly 35% of the total value and growing steadily at over 10% per year. How are the surplus byproducts from production, such as bamboo dust, fine powder, and fibrous fragments left after cutting, turning, and polishing, fully utilized? The answer lies in bamboo powder technology, a breakthrough that transforms all bamboo waste into a new source of bio-based material. All remaining fragments and bamboo dust are collected, dried, and finely ground into powder, with particle sizes ranging from 80 to 120 microns. This powder is then mixed with other ingredients. The company does not disclose the details, but the formula includes cornstarch, minerals, and a biological adhesive they call bioadhesive. Yet behind this innovation lies a complex reality, where science, safety, and policy often collide. The formulas for composite bamboo materials vary among manufacturers, and not all are safe. Since 2022, the European Union has banned the import of food containers made from bamboo plastic composites due to concerns about toxic chemical leakage, especially when exposed to heat. From a broader perspective, even traditional plastic containers pose health risks, with evidence showing they can disrupt hormones and reduce fertility. Therefore, if bamboo-based products are certified safe and truly biodegradable, they have strong potential to become a sustainable alternative to plastic. When compared to paper, recycled paper remains the best option, with a carbon footprint only 1/3 that of paper made from bamboo.